In this video, we're going to talk about confidence intervals for population mean when sigma is known, and we'll go through an example. But first, let's just talk about what the confidence interval for population mean is. All right, so somewhere on the number line, from negative infinity to infinity, there is a population mean. Okay, so somewhere on this number line, there is a population mean mu, right? The point is that the population mean mu is not restricted the same way that population proportion is. Population proportion is restricted between 0 and 1, but mu can be any number on the number line, right? Average can be any number on the number line. But for a particular population, there's one mean, one population mean, okay? And it's unknown, right? So what we do is we go out and we get a sample. And so say we determine, okay, well, here's X bar, here's our sample mean, and that's a point estimate, right? And then we want to construct some sort of confidence interval using that point estimate. So we go some margin of error in both directions, to the left and to the right of mu. Okay, so we go some sort of margin of error to the left and to the right of mu, and then say we're constructing a 95% confidence interval. Then we'd be 95% confident that this interval that I constructed contains mu, contains the population mean. All right, so let's go ahead and write that down. So we have X bar minus the margin of error. We're constructing the interval for mu. X bar plus the margin of error. Okay, so this is the confidence interval for population mean mu. Right, now, what's E? What's E? The margin of error is the critical value, so Z alpha divided by 2, times sigma over the square root of n. All right, so this is the margin of error equation. Now, in order to be able to use this confidence interval that I've put up here, in order to be able to use this, you need to have the normality assumption. You see how Z is involved in this calculation of the margin of error. So X bar must have a normal distribution. And there's two ways that could happen. The first way is that the data, or X, right, is normally distributed, right? Or the sample size, so sample size is more than 30, right? Remember, central limit theorem says that X bar will be normally distributed no matter what the original distribution of the data is, as long as the sample size, n, is greater than 30, okay? So if these two criteria are met, then you can use this formula. Also, if the data is normally distributed, so say n is, let's go two different possibilities. Say n is greater than 30, or n is large. Then the sample standard deviation, you can approximate the sample standard deviation to equal sigma. All right, so if the data is normally distributed, then whatever the sample standard deviation is, then you can approximate sigma. Actually, the same goes for if the data is not normally distributed and n is greater than 30, then you can use the sample standard deviation to approximate this sigma here. Let me draw that a little nicer. Sigma, right? So the sample standard deviation approximates sigma. But if the sample size is small, less than 30, then the data must be normally distributed in order to use this formula. But if the sample size is small, less than 30, then sigma must be known. Must be known. Okay? And why must it be known? Well, because sigma is involved in this equation for E. All right, let's go ahead and let's use this. Let's use this confidence interval. Let's construct a confidence interval in this example here. So in a sample of 100 Americans, their average height was 68 inches. The population standard deviation is known to be 5 inches. Find the 95% confidence interval for the population average height of Americans. Okay, so let's see. N, the sample size here, is 100, right? And a sample of 100 Americans. Their average height, okay, so this is the average of the sample, 68 inches. The population standard deviation, remember population standard deviation is sigma, is known to be 5 inches. Okay, now even if they gave us the sample standard deviation, we could still use that 5 inches is approximately equal to sigma, right? But they didn't give us the sample standard deviation. They gave us the population standard deviation. Right, but had they give us if they had said that the sample standard deviation was 5, then because the sample size is large, we could have said, okay, well, sigma then is approximately equal to 5, and I can use this equation for the confidence interval. Okay. Anyway, they gave us the population standard deviation, so let's just write that. Sigma equals 5. Find the 95% confidence interval. Okay, so we're trying to find 95% CI for mu, right, for the population average, so for mu. Okay, so I know I'm going to be using this formula, x bar minus E with mu in the center, and then x bar plus E. So I need to determine what's E first. Okay, so the equation for E, Z alpha divided by 2, sigma over square root of n. All right, I have sigma, I have n, I need to know what Z alpha divided by 2. So this is a 95% confidence interval. Okay, so 95% is in the center, which means 0.025 is in each tail, right? The entire area under the curve must equal 1, so that's half of 5% basically is in each tail. Here's Z alpha divided by 2, the critical value. All right, so the area that's behind that critical value is 0.95 plus this 0.025 plus 0.025, which is 0.975. So I have to look in my table to find 0.975, to find the Z value which has the area behind it of 0.975. Let's go ahead and go to our table. 0.975, 0.975. Okay, there it is, 1.96. So Z alpha divided by 2 is 1.96. All right, so this equals 1.96 times sigma, which is 5, over the square root of 100. Okay, square root of 100 is 10. Let's go ahead and pull out our calculator. Let's clear it out. So 1.96 times 5 divided by square root of 100 is 10, so just divide it by 10. Okay, equals 0.98. Equals 0.98. All right, so now let's go ahead and calculate our confidence interval. 68 minus 0.98, and mu is in the center, and 68 plus 0.98. All right, so let's go ahead and pull out our calculator for this. So 68 minus 0.98 is 67.02. All right, and then this will be 68.98, right, when we add those two together. All right, so we are 95% confident that the population average height of Americans is between 67.02 inches and 68.98 inches.